Oh, hey guys, what's up? Eddie Aho here with kissanalog.com. Hey guys, I'm measuring noise, and I just did a video where I compared switcher with the linear, right? Hey guys, I'm going to chat for a minute, kind of talk about the measurements, but what I'm going to do in this video is I'm going to show you why the last measurements I took are legit, okay? I got a little secret measuring device back here I'm going to show you. All right, stay tuned. Let's get back into this. This time we're focusing on the switchers since the noise was almost nothing on the linear, but we had some switching noise. And the funny thing is I love the comments down below. Guys, hit the comments. Hey, so I just want to mention that you guys have been on the channel for a while. You know this, that I'm a switching power supply. I'm a power supply engineer, been power supply engineer for many years. I did a video about my background, and that doesn't really cover the last 4 or 5 years or something. I've worked for a few different companies since then with another defense contractor now. Anyway, lots of VMI experience, lots of power supply experience. And when I did that video, I was just showing you the noise difference between a switcher and a linear, right? Some people thought, well, maybe you can't measure the switching noise the way you're doing it. And it's like, well, I didn't really want to get into how to measure noise and make the video about that. I was just trying to compare these two. Now, see this green terminal? That's chassis ground, right? There's chassis ground down here too. You find it on pretty much every power supply. But these two terminals are floating. And these two terminals are floating. So I was taking my scope and I was putting it on these two terminals. Well, I think some people are concerned about the common noise versus the, differential. Some people call it normal mode noise, and whether or not I was measuring it properly. Because there's been some talk about how to do that properly, and I should do more videos. I've done videos on ground, on this chassis. This is chassis ground or safety ground. Ties all these chassis together, makes them all the same potential. That's the number one important factor that it does. And that's why I like to call it safety ground. Now, in Europe, I think they call it PE, protective earth. And some people refer to this as earth ground here in the States. But the earth has very little, really, I could say arguably nothing to do with noise, okay? Some people feel like the earth ground's this quiet place where noise just like dissipates into. Thus, audiophiles will have these ground boxes with crystals and stuff, and it's just insanity, guys. Earth ground, crystals and all that have nothing to do with taking away noise from your electronics, okay? The only reason the chassis ground, the safety ground, is tied to earth is for lightning protection. That's the number one reason. Is to put the power grid all the same potential when you walk outside, when you get in your hot tub, whatever, okay? It's not a place to put EMI noise. EMI noise does not go that way. There's no path. Remember, electronics is about electrons, and electrons in a circuit are sitting still until a circuit is made, right? And when a circuit is made, that means it has a loop, has a place to go and come back to. That's just physics. That's just the way it works. Connecting something to earth, those electrons aren't going to earth ground to go somewhere. There's no circuit. There's no way for them to get back. But they do float around on these chassis. That's why there's EMI filters. Unfortunately, on these EMI filters, they use Y capacitors tied to your chassis. So it puts noise on the chassis, okay? That's why EMI filters have to do two things. One, they can't allow too much noise to get out on that power grid, on that line neutral and earth ground, safety ground, PE, that chassis ground, green conductor, okay? So That's half the job. The other half the job is to protect the device from the noise that is already out there. So if each device is allowed to put a little bit of noise on the grid, well, the EMI filter in here wants to protect that. Now, the thing is the noise generated in a power supply, it's right there. It's pretty, it's high energy switching. So the filter is designed to keep that going out. If it can keep that from going out, it can stop the smaller noises that are spread across a bunch of different frequency bands from coming in, okay? The chassis, however, has noise on it, okay? And I'll show you some other videos about how to take readings, how to tell if it's common mode or normal mode, differential modes, normal/differential mode. So I'll do some videos on that stuff. But for now, I'm going to, in the last video, I went to an isolated output, and I put a scope probe on it. And sure, the ground strap on the scope probe is tied to chassis ground, and I can touch these because I'm safe, because that's what safety ground is to make sure I don't get zapped by touching two metal things, okay? That's the whole purpose. So all those metal things across there, except for this one, it's got the little small signal that's under what they call the safe electrical low voltage, but all the other stuff's metal, and it's all tied to chassis ground, okay? Unfortunately, we call it ground. It just should be called chassis return. But the chassis is tied to my shield, and so my return is my chassis. So some people are concerned about that. But now think about it. This scope, or these power supplies, all the noise that we're seeing that I was showing you, for it to get out the power cord and to get into the EMI filter, this to get over here, that'd be quite a feat, and it's not going to do it. All right, so yeah, it's not going to happen. So that's why what I did was totally legit, and I was actually showing you the noise. Now the noise was amplified because I've got somewhat of an antenna, high impedance, and that's why I just talked about that ground loop. And they have the little springy clip things you put on the end of your tip where you go across, say, a capacitor or something to read the actual ripple. But this high frequency noise, I wasn't concerned with it. I'm still not concerned with it. And like I showed you, the electronics, when you plugged into, let's say you plugged into a different Class D amp, any kind of amplifier, even one as kind of poorly designed as this, it doesn't have any ceramic capacitors at the terminals. Pretty much any device, when you plug it in, even something like this, an aluminum cap, which is not very good for high frequency, even that, just because it does have some impedance, it does load it down somewhat, and there might even be some ceramics underneath the heatsink somewhere. It's been a while since I pulled one of these up, so I don't remember right now, but anyway. And then I showed you putting the ceramic across the terminals here, reduced it significantly because it's low energy. It's just high frequency spikes. They're very narrow, high frequency stuff, okay? And when you're doing that really high frequency stuff, the higher frequencies it is, the easier it is for it to propagate, right? But as far as your electronics, with all the filtering they're going to have in them, they're going to take care of that stuff, a lot of that. So it's not generally a concern. Even in audio, you can't hear it. It's not going to do anything. Class D amplifiers have a lot of that switching noise. It's not going to bother your sound. You can't hear it. It's not going to bother electronics. And anyway, so what I want to show you today is another test to show you that it was legit what I was doing, okay? And I've got a mixed sig scope back here. I got differential probes. Guess what else I have? Well, I got a little surprise probe over here, okay? So, you know what? Let's bring the camera over. I'm going to show you the setup. I'm going to show you the measurements. And let's see what you guys think about this, all right? Love the comments. Love the challenge. Love the, I like to see you guys comment and talk and chat between each other. And if I jump in, I just do it to try to respond to people to give them some feedback. But I hope I don't do it to keep others from responding and giving feedback. Sometimes I wonder if I am kind of causing some issues there. Maybe people think, oh, he's been answered, I'm not going to answer that. But no, please respond. Okay. All right, let's come over here, take a look at this. All right, guys. So when the power supply is on, my settings right now is 10 volts. We have an 8 ohm load, 1.2 amps, not very much, 12.4 watts. But just for the purpose of showing with no load, without any output, we're just getting the noise at the terminals, okay? Versus when we turn on this load, okay? So we're just going to look at these two things because I think that'll show, that'll demonstrate basically what, this noise thing I'm going to show you, okay? All right, guys, check it out. We're back to that 8 ohm resistor, 200 watt, right? Okay, and it's connected right here to this red and black lead that goes to the power supply. So we've got the scope probe right here, okay? Nothing fancy. I haven't tried to wrap it or anything, just connected like that. And then I've also got differential probes connected to it, okay, guys? And I've got a current probe, totally isolated. So high impedance differential probes here, and then totally isolated current probe. We're going to look at the mix sig because we have these probes connected to that. But first, let's go upstairs and see what we see up there. And then we'll come down to mix sig and see what we see, all right? All right, guys, so here we are at 5 milliseconds per division, and we have that noise we saw before. And I'm just going to zoom in, and we're triggering on this waveform here in the middle. So see my trigger right here? If I go right to the top, I can get it to go from that arrow to this arrow right there. Now, there's a burst, right? Let's just zoom in. Now, see, we have these high frequency things, right? They're pretty high frequencies, but let's keep on going. Now, we're zoomed in on one of those guys. Yeah, check it out. Pretty high frequency. All right, guys, so we zoomed in, captured the waveform, and it is 39.7 megahertz. Pretty darn high frequency, huh? All right, guys, so we're capturing this high frequency pulse, right? Now, the power supply is off still. Let me turn it on. Okay, we're 12 watts. Now, look, it comes down rest. Look, same thing. Same switching noise. Now, when we zoom out, it could be a little bit different, you know, from pulse to pulse. It might be more pulses or whatever. Here, look, right there, I'm going to turn it off. Problem is we have to wait for it to settle. See, it's got this little burst, right? And then off. So it does change, right? Now, let me turn it on again because we're getting more bursts because the converter has to regulate. So we're putting out current. So now let's zoom out a little bit more. See, now that's kind of what it looks like, kind of off and then on during this time and off. So kind of different shape, right? Okay, now that's 12 watts only. Let me turn it off. And now it's mostly off and then on for a little bit. And then, so what we saw in the last video is as I increase the power, it just kind of fills in these blanks. It has to run a little bit longer and then it drops off. And it almost goes right to the end before it does. And that, I think I went to a couple hundred watts, and this is a 600 watt power supply. So as we go higher and higher, pretty soon, you know, 600 watts, it would totally fill in, I would think. But still, here, let me freeze it right there. Okay. Zoom in on this stuff. And there we go. Same waveform. So that's a resonance caused by the transistor turning on and off. It's not going to change with power. That's just the on-off cycle, the sharp edges ringing against the capacitor and the inductance in the circuit there, okay? So that part is going to stay the same. What's going to change is how often it's occurring, But still, it's very low energy, guys. This is very low energy stuff, right? We're 200 millivolts per division, by the way. So let me turn it on and I'll let it run again and we'll zoom out. All right, so now let me show you something else. All right, guys, got the MixSig hooked up. It's running, and I can show you on my iPad so you can see the waveforms really well. Maybe I should do that. But what I thought I'd do is show you the same way I showed on the scope up here, just using this camera. So maybe we'll just do that for this video, okay? All right, guys, from this point of view, you can see this current probe here, the CP503. This is an awesome current probe. We have a manual range. We can go from 6 amps to 30 amps, or, you know, I've got other settings here on this probe. Very nice probes. Differential probe over here. Okay, guys, this is battery operated, okay? So we're isolated as well as using differential probe and a current probe, all right? All right, guys, so let's go ahead and I'm going to connect up the power supply. All right, so now what we're going to do is see what we can capture. I'm going to put this at 2 milliseconds per division, same as the other one, 2 milliseconds. Wow, look at that. That's amazing. Okay, so I'm going to turn off the current one. There's the voltage. Doesn't that look like what we were seeing before? Now this is 250 millivolts per division. I don't have a 200. I go to 500, I go 250 or 100. So I go to 250. So it looks a little smaller than what we saw in the Uni-T, but that's because Uni-T is 200 and this is 250. But imagine that. Now my trigger is on the current. Let me bring this down. Okay, so it's kind of all over the place. Had it on high frequency. Okay, so now it's just on AC. So yeah, there we go. All right, so now let's turn on the current probe again. Now the current probe is 4 milliamps per division. Now remember, the power supply is turned off. I'm going to zoom in on the screen now that you kind of see what I'm doing. I just want to show you the probes up here. All right, guys, we're kind of zoomed in again. I'm going to turn off the current so you can see that voltage again, 250 millivolts. And we're at 2 milliseconds per division right here. Okay, so very nice scope, very nice, you know, probes, all that kind of stuff. But look at that, guys. That's a differential probe. What the heck? I thought somebody said use a differential probe to get rid of that noise. Yeah. Okay, let me turn on the current. There's current. Okay, let's go to the current trigger. I'll move it up here, see if we can get it freeze a little bit better. And look at that. All right, guys, let's do the same thing. Let's zoom in on this bad boy. Hey, you know what? Should we show off a little bit? Let's use deep memory. We'll freeze it. We're going to show off and show the deep memory on this scope too. Whoops, hold on a sec. I got to get one of these waveforms. There's the arrow right there. All right, let's zoom in. There we go. Let's pull up the cursors, vertical cursors. Okay, let's move. Well, maybe I'll move the waveform over. All right, let's grab one of these guys and move it over there. I'm on the, I gotta click the yellow waveform. Okay, there we go. And what does this thing say? It says 40.65 megahertz. All right, guys, so now I've got these cursors. I'm kind of trying to set them up the same way I had on the Uni-T, right? I could get really accurate hitting these arrows, trying to move this around. Like trying to do something like that. But basically, it says 40.65 megahertz, okay? So if I zoomed it, If I zoomed out like this, 39.6, I think that was the same as the Uni-T. So just, you know, I mean, just moving those things slightly at this resolution is going to make a big difference. But there you go, guys. Crazy, right? Plus, aren't you impressed with that deep memory? Uni-T has it as well. They both have really nice deep memory where you can freeze it and then zoom in. So that's another little thing I wanted to show you on these scopes. How much, you know, why they're so many ways they're better than the old analog scopes. So there you go, guys. Oh, hey, you know what? Let's get running again, okay? Now we see the current voltage. You know they're out of phase a little bit. You know, there's a little bit of an inductive pickup with the current probe. And that's a high frequency. Even though this probe's a high frequency probe, there's a little bit of delay. I could set the delay on channel 4. So to adjust for that, to offset it, but you know, by setting up a delay. But yeah, we don't need to worry about that. Just wanted to point out that it looks like there's a little phase shift, right? And you can see how many times the scope is writing over and over and over. So when I freeze it, let's see, I think if I do it this way, yeah, it gets rid of all the previous waveforms and saves the last one. But that's just kind of an interesting thing that happens when you're watching. So if you want to do history, I mean, if you want to do that persistence thing, you could see how much it's changing and stuff over time. So that's kind of fun to do too. Okay, I'm going to turn on the power supply. Wow, really no change, right? Let's do this. No change, right? So I just wanted to show you that. Here, let's go ahead and let it run, and let's zoom out. Okay, there's the 2 milliseconds or 5 milliseconds we saw before. Let me turn off the current one, and look at the voltage. Doesn't that look the same as... Let's go back to the yellow trigger. Wow, doesn't that look the same as the Uni-T? I mean, they are very, very similar, right? So, yeah, here I am with differential probes and a current probe. Turn on the current. The current looks a little bit different than the voltage does, but still, yeah, I didn't have a current probe up there, but still, the point I wanted to show you with the current probe is that you still see the same noise as we did before. And let's see if 20 microseconds. Okay, I'm going to turn off the power supply, okay? Okay, now let's see. We got to get the trigger down here. So the amplitude drops a little bit, okay? But so it does, you know, the amplitude does increase a little bit, but the frequency is still the same, right? Still the same frequency of noise. There's less content overall, right? But I mean, the turn on and off frequencies are still the same. But there's less content as far as if we go back to, say, 2 milliseconds. I mean, you know, there's more of this solid noise with just bursts of on-off times. And there's a voltage, there's a current. So there you go, guys. All right, guys. So what do you think? Give me your comments. 2 big thumbs up to my patrons. Hey, if you want to buy me a beer I got a rant I want to do this weekend. So come on, guys. Jump in there and buy me a coffee, buy me a beer. Let's make this a good rant, okay? And yeah, I've got some... Anyway, we'll talk about it later, okay? Thanks for watching. 2 big thumbs up to my YouTube members, to Danny, my team member, my patrons, all you guys. Really appreciate the support. It's been flat for the last 2 years. I was looking at things with my wife, and it's like, man, tough times. It's like, and my software and everything, I had to get some more memory, some hard drives and that. Man, the cost of these things just keep going up instead of going down. So, yeah, it's been expensive. So, we're in it for the long haul though, but it has been a little bit of a stretch lately. So, anyway, thanks for watching, guys. Appreciate that. And free ways to support channels using the affiliate links down below and all that kind of stuff. And just giving a thumbs up to the video and let me know what you guys think. All right. Thanks for watching. And give me your comments, your ideas about what you'd like to see as far as noise goes and that kind of stuff. And I know that some of you guys want to see some filtering. We're going to definitely do that stuff. So let me know what else. Thanks for watching. We'll see you next time.